So, welcome everyone. This week, welcome to the Bangalore Theory Seminar Series. This week, we are excited to have Kazusato Oko as our guest speaker. Kazusato is currently a master's student in Department of Mathematical Informatics at University of Tokyo, where he is advised by Kazi Suzuki. He also belongs to the deep learning theory team at Riken AIP as a part-time researcher. He received his bachelor's degree and Dean's Award from University of Tokyo in 2022. His research interests include stochastic optimization, generalization of neural networks, and analysis of discrete structures. Today, he will be giving a talk about spectral sparsification of directed hypergraphs by Spanner's counterpart. And over to you, Khan.
Okay, so thank you for introducing me. And first of all, I would like to express my appreciation for Professor Luis for giving my opportunity for this presentation. And also I appreciate Professor Yoshida Yuchi for introducing me this seminar. So now I'd like to begin the presentation on hypergraph sparsification theory. I introduced my research results on near-optimal spectral sparsification of directed hypergraphs, which is a joint work with Professor Shinsaku Sakaue, he's here, and Shinichi Tanikawa. So note that I organized this presentation so that this also provides some basic overview of this field, including the definition of hypergraph sparsification, and the first algorithm by Soma and Yoshida, and some recent trends on undirected hypergraphs and other objects. I won't use any difficult prerequisites, so I hope you will listen to this presentation as a starting point for your interest in spectral sparsification theory. So first, okay. I cannot change the slide. I cannot go to next slide. How to change the page?
You're on.
Okay, so okay, now it's okay. So first, okay, as opening remarks, I will talk about what the term of sparsification means. So when you have a dense object with many elements, for example, a graph with many edges, or a matrix with many non-zero elements, applying algorithms to these dense objects will take a long time, and also the storage cost should not be ignored. So to address these issues, sparsification is a procedure to obtain a sparse object that approximately preserves some important properties of the original dense object. And using a sparsified object as an input to the algorithm instead of a dense one, we can speed up algorithms without loss of accuracy. And this is indeed a very powerful technique. And in fact, for example, edge sparsification of graph has helped speeding up various graph-based algorithms, including graph neural networks and fast solving of Laplacian systems. So in this talk, we focus on spectral sparsification of hypergraphs, which is an extension of graph sparsification, and putting a little more weight on directed hypergraphs. To understand the motivation and definition of hypergraph sparsification, following the history, we brush up usual graph sparsification. In both usual and hypergraph cases, the key conserved quantity is energy function. So we first see how it is derived in the ordinary graph case, starting from the definition of cut weight. Okay, so let us consider undirected and weighted graph G on the vertex set S of V, vertex subset. So we call some edge is cut by vertex subset S if one side of the edge belongs to S and the other does to the complement V minus S. The cut weight by S is the sum of edge weights over all edges cut by S. So in the sphere, it is 3 plus 2 plus 4. So it's equal to 9. And it is easy to see that a cut weight has this another representation where 1s is an indicator vector whose dimension is n, or the number of the vertices, with all 1 in coordinates corresponding to s and all 0 in the others. Then we define the energy function as this, as an extension of cut weight function to the continuous domain of all real valued n-dimensional vector. So it is a function of n-dimensional real valued vector, where each coordinate corresponds to each vertex of G. And for each edge between U and V, we compute the square difference of xu and xv and multiply it by the edge weight. This part is sometimes called as the energy of the edge E. Then we sum up this quantity of the edges and obtain the value of the energy function. And we remark that this energy function can be written using some positive semi-definite matrix LG called graph Laplacian, but in the hypergraph cases, it cannot. Okay. So then we define spectral sparsifier of graphs. Given a possibly dense graph G, if some other graph to the G has approximately the same energy function value as that of G, we say to the D is a sparsifier of G. And more precisely, when the error is bounded up to some multiplicative factor of epsilon, then we call to the G is an epsilon spectral sparsifier of G. And note that if the error guarantee holds, not for all real valued vectors, but for all binary vectors, so which takes only 0, 1 value, then it means that all cut weights are actually preserved. So we say to the G is an epsilon cut sparsifier of G. And also, I introduced some well-known results on graph sparsification here. It is known that there exists epsilon spectral sparsifier with size n over the square epsilon up to some logarithmic terms exist. And we mentioned several constructions of the spectral sparsifier. The first one is due to Spearman 10. It suffices to sample every edge independently with some probability defined here. And here, this part is sometimes called the effective resistance of the edge E, and which we can say that which corresponds to some importance of each edges. And the proof follows from some linear algebra, like matrix Bernstein inequality. The other method is due to Cortes and Shu, which we call spanner-based sparsification, and we utilize this algorithm later for hypergraph sparsification. The algorithm is simple enough and just a repetition of the following procedure. At each step, we take a bundle of spanners. A bundle of spanners is constructed by first taking one spanner of the input graph, and then for the remaining part of the graph, we construct another spanner, and we iterate this process, which yield a bundle of spanners.
Kazu, could you just remind me what these spanner graphs are?
Could you speak more slowly, please?
Could you remind me what these spanners are?
Oh, spanner is in this definition, spanner is a subgraph of G, which preserves approximately the distance between each edges U and V. So in this case, we take log n spanner. So this means that the distance between each edges can be preserved up to log n multiplicative error. Is this clear now? Okay.
Okay.
Yeah, thank you for asking the question. And yeah, after the bundle of spanner is taken, we sample the remaining edges with fixed probability. And iterating this finally yields the desired sparsifier of the linear size about this order. And we also mentioned other constructions, iterative partitioning and sampling that is used in the seminal work of Spielmann and 10, and the use of barrier functions, which makes sparsifiers deterministically, and SPP-based one, so which removes logarithmic factors from the sparsifier size. Anyway, undirected graph sparsification has been well established and widely used in application. So now we proceed to spectral sparsification of hypergraphs. We first define the energy function. An undirected hypergraph is a set of vertex set V, a hyperedge set F, and a weight function Z. The important difference is that hyperedge is, unlike usual edges, a subset of a vertex set V and allowed to contain more than two vertices so that each hyperedge can represent relationship between multiple objects, like in this figure. And this time, we define hyperedge F is cut by a vertex subset S if F shares at least one vertex with S and at least one with the complement. So in this figure, F1 is cut, but F2 is not. Then we consider the weighted sum of hyperedges cut as cut weight. So this can be written in this way, alternatively. And in this part, for each hyperedge F, we take the maximum of this quadratic value for all vertex pairs in F. Then we extend the domain to all real value vector X, and we get the definition of the energy function of undirected hypergraphs. And one thing to be noted is that this is quite nonlinear due to the maximum operation. So this prevents us from using linear algebraic tools like matrix Bernstein inequality and makes sparsification and analysis more difficult. And also note that if all hyperedges contain just two vertices, then the energy function is exactly the same as that defined for usual graph. So in this sense, this can be seen as an extension of usual graphs. And on the other hand, directed hypergraphs are generalization of directed graphs. So this time, a hyperedge is a set of two subsets of V, so where each of two is called a head and tail. And in usual directed graphs, edge is a pair of head and tail, like this. So T, E, and HE and TE. But each of two is just one vertex. But in this case, we generalize to each head and tail contain more than one vertex. Okay. Then, as usual, we define cut weight. Following the definition for directed graphs, we say a hyperedge F is cut by S if the tail of F shares some vertices with S and the head shares some vertices with the complement. So in this figure, notice that S does not cut a hyperedge F2 or F3, even when F3 crossing the border, but we do not say F3 is cut by S. So here, the only hyperedge which is cut is F1. And we can consider the cut weight as a weighted sum of hyperedges cut. And now we can proceed to the definition of energy function. So first, the cut weight function is alternatively written in this form. And the plus symbol in here denotes the real function, or the maximum of the input y and 0. Then you can see that this form is actually alternative definition of cut weight. So this inequality holds. And we extend this cut value to all range of x and obtain the definition of the energy function of directed hypergraphs. And this is further nonlinear even compared to undirected hypergraphs. So this is quite nonlinear, and as evidence, Directed hypergraphs include all undirected hypergraphs by letting the tail and head all the same for all hyperedges. So meaning that this holds, okay, this holds for all hyperedges. Then this energy function is the same as that of undirected hypergraphs. And we can show that the lower bound, which quadratically depends on n, so the lower bound exists. So which essentially distinguished directed hypergraphs from undirected hypergraph, since undirected hypergraph has a bound linearly on n. And also, this is a bit off topic, but directed hypergraphs are complex enough to represent a wide range, a wide class of submodular functions as a cut weight function of some directed hypergraph. And if you are interested in this, we recommend you the work of Soma and Yoshida or our paper. So now, we introduce the definition of spectral sparsifiers of both undirected and directed hypergraphs. So as in the graph case, given the hypergraph H, we say Tudor H is an epsilon spectral sparsifier of H if the energy function of Tudor H preserves the energy function of H for all x up to multiple recursive factor of 1 plus minus epsilon. If this holds for only binary vectors, we say Tudor H is an epsilon cut sparsifier of H. And we provide brief literature review here. The spectral hypergraph sparsification is initiated by Soma and Yoshida, and we will introduce their algorithm later. Their bound is a third power of n. Since the number of hyperedges can be as large as, exponentially large with respect to the vertex set size, so this can be as large as this or this. So this polynomial bound is already surprising and non-trivial. But however, since then, many foreign works try to reach the optimal bound, especially on the dependency on the vertex set size n. And for the undirected hypergraphs, Banzhao et al. And Kapralov et al. Improve this bound when the rank of hypergraph or the maximum number of vertices contained in each hypergraph, hyperedges. So the rank is defined as this, generated by R. So if this small, we can improve the bound of Soma and Yoshida. And last year, inspired by the improvements on cut sparsifiers, and Kapralov et al. Established finally the linear size bound, so with no dependence on R. And recently, epsilon dependency has improved by 2 independent works. Okay, so this is an overview on undirected hypergraph sparsification. On the other hand, for directed hypergraph, also Kapralov et al. Proved rank-dependent bound for the directed hypergraph with uniform weight, means that all hyperedges should have a constant weight, and roughly improve the bound on cut sparsifiers. But the bound of quadratic dependency or n, without depending on the rank R and for general weight, has not been obtained. So this is where my result contributed to, and we obtained the bound of n to the power of 2, so without depending the rank R. And this bound is obtained by using spanner-based sparsification framework of Cortes and Xu as an algorithm, and in the analysis, combining chaining type argument and combinatorial observation in the analysis. So rather than just following the proof, in this presentation, I would like to explain the difficulty in dealing with a nonlinear energy function and essence of chaining type arguments that are also common in all undirected hypergraph sparsification. Okay, so in the next 10 minutes, we introduce seminal work of hypergraph sparsification by Soma and Yoshida. Which is not only the first work, but also I think is very helpful to understand the essential difficulty that resides in hypergraph sparsification, or how nonlinearity prevents us from using linear algebraic tools. So now I'm showing the algorithm for undirected hypergraph sparsification. The algorithm first computes for each vertex pair U and V sum of weights are hyper-edges that contain both U and V. So if we fix U and V and take the summation of hyper-edges that contain both. Okay. Then using that value dh, we define the sampling probability for every hyper-edge and conduct an independent sampling. And we construct the output sparsifier consisting of sampled hyper-edges in step 3 by defining the hyper-edge weight by the inverse of sampling probabilities. So this weighting maintains the value of the energy function for each fixed edge x in expectation. So for directed hypergraphs, they propose a similar algorithm. The only difference is that we cannot identify a vertex pair U and V. So in the first line, we compute the sum of weights over the hyper-edges with U in the tail and V in the head. So HF and TF. Then such hyper-edges can be counted, but the reverse case cannot be counted. Okay. So then we can define the sampling probability and conduct random sampling as previously. So now we briefly look through the proof strategy of the algorithm. Since there are little differences between undirected and directed cases in the analysis, so we focus on the undirected case, taking a little different route from the original version to shortcut the proof. Okay. So first, notice that if we limit the domain of X to a subspace where ordering pi of elements of X is fixed, for example, in the range, the ordering is fixed like this. So we only consider in this region. Then in this domain, the ordering or element defines which vertex pair gives the maximum value for each hyper-edge energy. So we can eliminate maximum operators and write down the energy function of the hypergraph into that of ordinary graph. And this corresponding graph consists of edges, each of which corresponds to a hyper-edge of the original hypergraph, and connect the vertex pair where the maximum is achieved and has the same weight as that of the corresponding hyper-edge. Okay, so we say this corresponding graph G pi. And similarly, following this rule, for the ordering pi and for the output hypergraph to the edge, we can also consider the corresponding graph to the G pi. So the important point is, if to the G pi is an epsilon spectral sparsifier of G pi for all orderings pi, then we can say that to the H is also the desired epsilon spectral hypergraph sparsifier of H. So all we need is to check whether to the G pi is a sparsifier of G for all ordering pi. However, note that the sparsification process is probabilistic. So thus, in order to show the uniform bound on the failure probability with delta over all pi, since the ordering has a factorial of n, so the failure probability for sparsification of each G should be smaller than delta over the factorial of n. So based on this discussion, we can interpret the sampling probability defined in the algorithm. So the sampling probability of a hyper edge F is bounded by this quantity in the undirected case for all pi. And this is a sufficient condition on sampling probability so that pseudo G pi should be epsilon spectral sparsifier of the ordinary graph G pi with failure probability less than delta over the factorial of n. So, and this factorial appears in this log term and finally affects the sparsifier size by order n. So you can refer Spearman and Sen for ordinary graph sparsification part as we proceed. And we can bound the number of hyper edges in the sparsifier as this. And due to the limitation of time, we skip this part, but we obtain the sparsifier of size, which depends third power of n. Okay. So in order to obtain tighter bound, we need to consider where we incur order n factor. So in directed hypergraph sparsification, there exists a trivial bound, lower bound of the square of n. And this is easily obtained by considering the bipartite directed graph. It is even not a hypergraph. So where each vertex pair between two vertex sets has an edge like this, like clique, with equal weight. And we can extend this bound to the square of n over epsilon. So we can obtain this bound by utilizing the nonlinearity of energy function of direct hypergraph. Anyway, however, the obtained bound by Soma and Yoshida is just cubic of n. So meaning that we did a weak bound in somewhere in the proof. So to identify where they did weak bound, notice that even for fixed f, the quadratic dependency on n is necessary to obtain bound. So thus, the point will be how we dealt the ordering of elements of x. So here we take a simple example. So if the first element of x is exactly 1, but the second element witnesses some fluctuations. So this fluctuation does not change the energy of each hyper edge that much, but in the previous proof, we regarded these two ordering as completely different. So this is why we need to bound the failure probability in each ordering with probability with a quite small probability at most delta over the factorial of n. Then which finally yes additional n dependency. So therefore, it is probable that this bound is too pessimistic, and we might have another route. So meaning that possibly it is not necessary to consider each ordering as the factorial of n ordering as completely different. However, what is difficult is that as long as we resort to linear algebraic tools, we need to fix which vertex pair takes max for all hyper edges, and necessarily to bound the failure probability with a quite small probability of delta over the factorial of n. So thus, in order to obtain tighter bounds, we have to leave from linear algebraic tools, and we need other more flexible tools discuss concentration of random variables. And based on what we discussed by now, we finally present our results on directed hypergraph sparsification. The key technique in the analysis includes chaining type arguments and combinatorial observation on directed hypergraphs. And these two components can be carefully and elegantly combined using the algorithmic framework of spanner-based sparsification by Cortes and Xu. And what I'm showing in this slide is the original spanner-based sparsification in the formal version. And this is quite simple. Given a graph G, then you iteratively construct smaller and smaller graph GT. And at each iteration T, the algorithm, as I explained, first deterministically keeps a bundle of spanner. Spanner here means which preserves the distance between any pair of two vertices with a logarithmic factor, logarithmic error, and we sample the remaining edges independently with probability 1/4. And if sampled with the weight of that edges quadruples and added to GT. So after one step of this process, we obtain a roughly a sparsifier of size roughly 1/4. And taking this process over the order of log n times, we finally obtain a roughly linear size output. And this is a mechanism of the framework by Curtis and Xu. And a virtue of this algorithm is simplicity, because it is easy to incorporate combinatorial observations since we do not need to adjust sampling probabilities as algorithms I explained before, but it is fixed, rather fixed to a constant. In this case, it is 1/2 or 1/4. Okay. So we found that this simple algorithm is indeed helpful in directed hypergraph sparsification, where combinatorial observation plays crucial role in reducing dependency on n and rank R. And we remarked that this algorithm has been extended to parallel sparsification and full-train sparsification. And using this framework, we can also show that such extensions can be done for hypergraphs, but we omit the detail here. Okay. So based on this, we propose the following outer loop structure for directed hypergraph sparsification. So at each iteration, we first take a small number of hyper edges, ST, and which corresponds to a bundle of spanners used in Curtis and Xu. So we call this subset as a quartet and explain in the next slide. But all the other parts are essentially the same as the original algorithm. So in the next slide, in this slide, we define spanner's counterpart in the following. For each U and V in the vertex set, we take lambda heaviest hyper edges among those not taken yet, and with U in the tail and V in the head. And here lambda is a parameter which controls sparsification error. And we added these hyper edges to the set S. And after we iterated this step for all vertex pair, we return S as a quartet. Okay, so we back to the slide. And we now turn to the analysis of the algorithm.
Okay. Sorry, so how much time do you repeat this, removing the heavy edges?
Oh, to take enough. So you're asking the order of lambda, right?
Oh, this is done just once. Oh, for every vertex you do it. Okay, okay.
Oh, okay. So first for the lambda, as we show later, it is taken in this order. So it's 1/the squared epsilon, right? So it has no dependency on n. And for the sparsification process, the outer loop, if the number of hyper edges is as large as exponentially on n, then we have to iterate this process about n times. But we have several. We can several tools to reduce this iteration time to logarithmic order, or we have other tools to prevent the error accumulates during the sparsification. So yeah, for simplicity, you can assume that this process is conducted only logarithmic time. Yeah. So the simplest way is to use existing sparsifier, for example, a Soma and Yoshida, which can produce the polynomial size sparsifier for the first time, and then if you this use this algorithm, then it is no need to iterate this n times. So all you need is a logarithmic iterations. Okay. Thank you for asking. Okay, so we move to the analysis. Maybe this slide is okay. So we move to the next slide. And we now turn to the analysis of the algorithm. We use the chaining technique on hypergraph. Firstly used by Kapralov et al. In this context, and now widely used in sparsification. I think understanding this technique is really important for reading other, understanding other hypergraph sparsification papers, and that is why I take enough time here. So let H be a hypergraph from the previous steps in our algorithm, and should H be an output of the current step. So we omit the, subscript T for simplicity, and we focus on to bound the sparsification error at one step. And without loss of generality, we can limit X to the range where the energy of X is just 1. Because whether the sparsification error, the multiplicative factor of epsilon holds or not, does not depend on the, how can I say, if you multiply some factors to X or not, okay? So in our case, since the sample probability is 1/2, the error can also be written in this way, So, and we need to show that this is smaller than epsilon. And here, epsilon f is a random variable taking plus minus 1 with probability 1/2 each. And rather than using linear algebraic tools, we discretize the value of x in more refined way so that we do not have to consider as many cases as a factorial of n. So let D be a set of discretized value x such that the energy of H is 1. And we try to obtain high probability bound for each fixed discretized value and then take a uniform bound. So the first time, the error can be bounded in this form. And the first time can be derived from uniform bound over sparsification error on each point of D. And the second and third terms are fineness of the discretization. So as the number of discretized value increases, the first term decreases, but the second and third term increase. So how to discretize? As the number of discretized value increases, the first time increase because we need to take a uniform bound in more complicated space, but the second and third term decrease because we have more points to approximate. Okay, so thus the how to discretize the space is quite important to balance these first and second third terms. Is important to obtain tight bounds. And to control this trade-off, chaining gives a way to construct progressively finer and finer rounding schemes. So we continue to use this slide. Okay. So in other words, not to consider the sparsification error at once, we first classify hyperedges to logarithmic number of classes. So we limit the hyperedge to some its subset like this. Okay, a subset A, and in other words, not consider the sparsification errors at once. We first classify hyperedges to some logarithmic number of classes and say one of such class as H, A, and then we consider different discretization schemes for each class. Okay, so if we subscript each class as AI, then we change the discretization scheme for each AI. So this enables us to discretize hyperedge values more adaptively, and intuitively, this is a key to balance this trade-off. And such idea is common in statistics, but as a target space, usually Euclidean space is considered. So this time, for hypergraph sparsification, we need to construct such rounding scheme looking at the structure of hypergraphs. And here we summarize how chaining type argument goes. And note that this will fail. This only fails because we need several additional arguments. But this slide will help you to understand how chaining arguments on hypergraphs is done in general. Okay, so we proceed. So first, we classify hyperedges according to its energy. So we are fixing the QHX is 1, so we are regularizing X. So for fixed X, the class FIX is defined as a set of hyperedges with energy of 2 to the power of minus I to minus I plus 1. And we consider sparsification error within each class. So we use different discretization scheme for each FIX. Under the energy regularized to 1, the hyperedge with large energy affect more on sparsification error because their energy is large. But on the other hand, there are few such hyperedges because we are regularized such that QHX equal to 1. Okay, so on the other hand, a hyperedge with small energy can exist more, meaning that more discretized values are needed, but we do not much effect. There's not much effect on the sparsification error since it is small. The energy is small. So utilizing this trade-off, we can obtain sharper bounds. So we sample each hyperedge is probability 1/2. So usual chain of 1 yields sparsification error for fixed F and within the class Fi bound as this. So the failure probability can be bounded as this within each class. On the other hand, let us consider the number of possible combination of the set FIX. Since hyperedges with energy approximately 2 to the power of minus I, and at most i's power of 2, so the number of at most i's power of 2, so the total number of combinations is about n choose i's power of 2. So this is the possible combination of FIX. And using this, the total number of discretized values are bounded, roughly bounded as this. So if we multiply the failure probability for each X, for each fixed X and FIX, and possible combination, possible number of combination, then we obtain this bound. So for epsilon smaller than 1, the failure probability exceeds 1, maybe, and meaning that we cannot guarantee the success of one iteration, successful sparsification of even one iteration. Okay. But in summary, a foundation of chaining type argument in hypergraph sparsification is like this slide, a classification of edges according to the energy, as we did in this slide. But the chaining argument itself does not suffice to produce epsilon spectral sparsifiers when epsilon is smaller than 1. And as many existing work, we need import other perspectives that enables a little more sophisticated construction of discretized rules. And in our case, it is a combinatorial observation together Curtis and Schu's framework, spanner-based sparsification. So we incorporate combinatorial observation into chaining argument. So let us utilize the fact that the remaining hyperedges are not sampled in the first step of the inner loop. So since the concept literally means important hyperedge subject, the remaining does not have large energy. So we use this part. And moreover, our counting argument does not depend directly on each hyperedges, but rather based on the critical pairs. Given X and fixed hyperedge, a critical pair is defined as a vertex pair which takes the maximum and gives the energy of that hyperedge. So the critical pair is defined like this. If there are more than two possible pair of vertices that takes a similar value, then we prepare some type breaking rules to define the UV uniquely. Okay. And one observation is that even if the size of Fi is large, we can show that the number of critical pairs of the remaining hyperedges is bounded with much sharper inequality. So in other words, when we exclude lambda coset from probabilistic arguments, they are sampled deterministically. The remaining hyperedges in FIX shares the same critical pairs in this in this figure. And in this sense, heavy hyperedges are localized. So here there are three hyperedges, but we are characterizing in this figure. We are showing in this figure that the green hyperedges share the same critical pair, U1 and V1. So this happens actually in the process of sparsification. And we formalize this observation in mathematical expression. First, we change the definition of class FIX a little by excluding hyperedges and deterministically taking lambda coset. Then, for the hyperedges of FIX with new definition, we count the number of distinct critical pairs. So this is at most I⁻²⁵ over lambda. So we can easily explain this. So for each critical pair UV, there exists at least one hyperedge F in FIX, and the maximum is taken at UV in the energy function. And remember that we added the heaviest remaining hyperedges at the time of construction of lambda coset here. So then we can say that lambda coset contains at least lambda hyperedges which are heavier or have equal weight as F. And these hyperedges have actually more energy than F in the specified X. And moreover, we took the coset so that we can choose such heavy hyperedges distinctly for all vertex pair UV. So this means that for each critical pair, there exists lambda hyperedges with energy more than minus I⁻². So we obtain that we can bound the number of critical pairs in Fi by at most this value. And we conduct our counting argument on these critical pairs. So this is much smaller than the I⁻². So we can obtain the tighter bound. So finally, we discretize the energy of hyperedges which share the same critical pair in a unified manner. So we do not directly discretize the whole energy, but we discretize the quadratic difference between U and V. And since ZF does not differ so far, this strategy works well. And for each critical pair, we can show that we need only a polynomial size list of discretized value to make the discretization error smaller than epsilon. Okay. So we conclude our analysis in this slide. Counting the critical pairs, the number of critical pairs is at most I⁻n over lambda. Over lambda is quite important. So this can be lambda times smaller than when we count based on the number of hyperedges. And for each critical pair, at most polynomial size discretization, it suffices. So thus, since the failure probability for one point is bounded just this, And the number of possible discretized value list is at most this. So here exists a lambda in the denominator. So multiplying these sums, we get the upper bound on the failure probability as a uniform bound for FIX over OX. And then taking lambda to 1 over the square of epsilon, we obtain epsilon spectral sparsifier. And since lambda coset contains hyperedges of at most lambda times square n, because for each vertex pair, we take at most lambda hyperedges, so the size of lambda coset can be bounded as this. So we obtain the quadratic size bound in directed hypergraph sparsification, so which is near optimal in terms of m. And before finishing this presentation, I mentioned some recent advances on the sparsification theory. So several works are omitted in this slide, but the spectral property of hypergraph Laplacian operator, which is a nonlinear operator closely related to the energy function, is analyzed for both undirected and directed hypergraph. And one thing as a recent advancement to be noted will be Kapralov et al. Achieves linear size bounds on undirected hypergraph sparsification. And this is based on chaining augment, but other than that, they made a weight balancing technique which relate hypergraphs with corresponding graphs to decide sampling probability of hyperedges. And this argument is further defined by two independent groups. I think this argument is simpler, so I recommend the beginners to read that for graphing undirected hypergraph sparsification. And also note that sparsification is extended to other objects. Lafay and Yoshida propose sparsification of some of submodular functions, meaning that if we have a set function consisting of some enormous number of submodular functions, you can single out important elements using sparsification theory. And also, hypergraph sparsification theory contributes to motif cut sparsifiers. This is a quite recent work. And as for application of hypergraphs, there have been many recent extensions of graph-based machine learning methods to hypergraphs. For example, semi-supervised learning using the energy function as a regularizer, and several hypergraph counterparts of the graph neural networks, where the Laplacian in graph neural networks have been replaced by hypergraph, has been proposed. Okay. So we now conclude the presentation. So first, we summarize the topic we mentioned in this presentation. So I first introduced the basic concept of hypergraph sparsification, and then moved to the algorithm by Soma and Yoshida, and show the difficulty in hypergraph sparsification, that is, limitations of linear algebraic probability bound, which comes from nonlinearity of the energy function. Then we proceeded to chaining argument in hypergraphs. And as for our bound, we proved the first near optimal quadratic spectral sparsification of general directed hypergraphs without depending on the rank and hyperedge weights. So our bound can be obtained by utilizing Cortes and Schu's spanner-based framework, to which we incorporate combinatorial observation to construct tighter discretization in chain. And the presentation is that's all. So, okay, so do you have any question?
Okay, let's thanks Kazusato for the presentation, and yeah, you can have questions now. So I wanted to ask one basic question first, like what are there any differences in the bound zone for directed graphs between directed graphs and undirected graphs? Is there any difference for these ones, or are these?
Could you speak more slowly?
Sorry. So I wanted to ask for if you compare directed graphs and undirected graphs,
Mm.
do you get same results for spectral sparsification, or is
Oh,
there some difference?
yeah, actually our bound is valid for undirected hypergraph, but for undirected hypergraph, we can obtain a linear size bound of n over the squared epsilon.
And
So,
for directed graphs,
mm,
for directed graphs, that
graph we can obtain the lower bound of
okay.
as large as this. So yeah, usual directed graph have at most
Mhm.
squared and not squared and edges, but using making use of nonlinearity, we can obtain the over epsilon. We can insert epsilon dependency on this.
Okay.
And this is also our contribution.
Okay. Interesting.
And we also note that our specification, if we replace the core set with a hypergraph counterpart of spanners, undirected hypergraph counterpart of spanners, then we obtain the bound about this size
Okay.
in the framework of Van Zyl et al.
I see.
Yeah, but in drop the dependencies on R, we need a more careful argument on defining the sampling probability.
Okay. Also, this core set, is it like used in other hypergraph problems, or can it be used to, what kind of other hypergraph problems could it be used to? Or?
Sorry?
So I wanted to ask this idea of this core set. Is it like has this been used for other hypergraph problems, or can it be used for some other kind of hypergraph problems as well?
So could you repeat?
I wanted to ask about this course, the idea of first sampling these core set. Uh, has it been used for other hypergraph problems as well?
So you mean the sorry? So the idea of sampling course, no?
Yes. Has it been used for other hypergraph problems?
So has been used other than the area of hypergraph.
Sparsification. Yes,
I
yes.
see.
So are you asking whether this framework is used in the hypergraph classification previous works? And the answer is no. So yeah, this is a quite simple framework, but all the other hypergraph work, especially undirected hypergraph classification, was mainly a one-shot sampling based on the effective resistance of corresponding graph. But we found that the Cortis-and-Schultz framework is very useful to incorporate a combinatorial observation, like we did about core set. So since the sampling probability is fixed, all we need to do is to singling out the important subset of hyper edges rather than trying to adjust the sampling probability more in more refined algorithms. So this is quite easy, and I think this is also the virtue of framework of Cortis-and-Schultz in the hypergraph. But none of the existing work use this taking this route. So this is my answer.
Yeah. Okay. Yeah. Are there any other questions? Okay. Since there are no other questions, let's thank the speaker again and I stop the recording.